Hi everyone. The another function we can consider as impulse function. Here the impulse function is a signal of infinite amplitude and zero duration. This is practically not possible infinite amplitude at zero duration. But in general, an impulse signal does not exist. But some circuit signals, in few cases, we can come very close to the approximating this definition, which is having higher magnitude instead of infinite magnitude, higher magnitude and close to the duration. That is nothing but for short interval, if you are getting the higher magnitude, that is called as impulse signal in practical cases. Due to the switching operations, generally when we turn on and turn off the switches, during that time we'll get this impulsive voltages. Short duration we can experience that higher voltages and higher currents occur in that circuit analysis, that is called impulse signals, like that we can assume, because those are close to that definition of the impulse. The impulse function enables us to define the derivative at discontinuity. At discontinuity means whenever you are turning on and turning off, the voltage and currents may go from 0 to higher voltage or higher current to 0 current, like that. Those are called the discontinuities, right? So we can find the derivative at the discontinuity. To define the derivative of a function at discontinuity, consider the function varies linearly across the discontinuity as shown in the figure. Just to find out the definition and mathematical representation, I am assuming here the impulse function f of t, which is varying across this time interval linearly around that 0 point, that I'm assuming it as, instead of considering 0 minus 0 plus, this is your 0, right? 0, this is 0 minus 0 plus. That 0 minus, I'm assuming it as minus epsilon, which tends to 0, and here it is plus epsilon, which tends to 0 only. So here it is varying linearly from minus epsilon to plus epsilon. That is my assumption. Here epsilon tends to 0, and when we differentiate the function, the derivative between the minus epsilon to plus epsilon is constant. When you differentiate this, obviously if linear is derivating, you'll get the constant. So derivative between the minus epsilon plus epsilon is constant at a value of 1 by 2 epsilon. How do we get that? That also we'll see. For example, if that is nothing but, you need to find out that area only, right? So if you are differentiating, how do we get that 1 by 2 epsilon? To know that, you find out the equation first. So if you find out the equation by knowing the coordinates of minus epsilon comma 0 and plus epsilon, this is x comma, what is the y magnitude? 1. Unit impulse function, here I am assuming, plus epsilon comma 1. By knowing these coordinates, by assuming this as x1 comma y1, x2 comma y2, we can write down that equation, right? Like earlier, y minus y1 is equal to y2 minus y1 by x2 minus x1 into x minus of x1, x minus x1. So here x1 y1 is equal to minus epsilon comma 0, and x2 y2 is equal to epsilon comma 1. Y is nothing but f of t, x is nothing but t. That's what I have substituted in this equation, so that I'll get the equation f of t is equal to 1 by 2 epsilon of t plus epsilon. I can rewrite this equation by sending this 1 by 2 epsilon inside this bracket, like 0.5 into t by epsilon plus 0.5. 1 by 2 can be written as 0.5. Or the same thing I can write, either I can, because the same slope linear, right? I can consider from here to here or from here to here also. In both ways I have done this equation. If you do the same thing, you'll get the same equation. So if I do the derivation of this function, f dash of t is equal to differentiation of f of t. Differentiation of f of t means f of t equation is this one. So differentiation of this function is, this is constant 0. Differentiation of time is nothing but 1. So 0.5 by epsilon. 0.5 is nothing but 1 by 2. 1 by 2 epsilon. So 1 by f dash of t function can be represented in a pictorial form like this. F dash of t is equal 1 by 2 epsilon, which is varying between the minus epsilon to plus epsilon. and f dash of t magnitude is 1 by 2 epsilon. If you find out the area of this function, area is nothing but length and breadth. So area is equal to 1 by 2 epsilon, because the difference, the height magnitude is 1 by 2 epsilon, and width is here epsilon minus of minus epsilon is nothing but 2 epsilon. 2 epsilon will get cancelled, 1 you'll get it. So for unit impulse function, you are getting the area as 1. So here few observations, like when epsilon tends to 0 or when epsilon approaches to 0. Epsilon is approaching 0 means 1 by 2 into 0. So which will reach to the infinity magnitude. At the same time, the duration of this large value is approaching to 0. This difference, when epsilon tends to 0 means minus epsilon will go to 0, epsilon will also go to 0. The duration becomes 0 and magnitude will become infinity. So it is the definition of that impulse function. The area under the f dash of t between the minus epsilon to plus epsilon remains, or plus or minus epsilon remains constant as epsilon tends to 0. Here we are reducing the magnitude, reducing the duration, increasing the magnitude. The area, however, it is same only. It is denoted with the del of t, and the derivative of f of t at the origin approaches a unit impulse function as epsilon tends to 0. So f dash of 0 is nothing but it is similar to the impulse function definition. That's why we will consider it as del of t as epsilon tends to 0. And the mathematical representation of the impulse function is integral minus infinity to infinity. Over the time interval, if you are integrating with some k into del of t, I am assuming that magnitude as k instead of unit impulse, k into del of t is equal to k. If it is unit impulse function means k will become 1, and the magnitude becomes 0 other than t is equal to 0. That means we have seen already the function, you'll have the magnitude only around the 0, or at 0 you'll have the magnitude. Impulse function means other than 0 the impulse function is 0. That means it can be expressed like this: the area under the impulse function is constant and it represents the strength of the impulse, like k magnitude at 0. F of t is equal to del of t, k into del of t, if it is having k magnitude. If it shift right side with some a time, then the same thing can be represented with k into del of t minus a. We have seen in the step function also. If it shift right side with some a magnitude, the k into del of t can be represented k into del of t minus a. So the same thing we can use it during the problems also. So if you see here, we'll see one problem based on this impulse function. Find the area under the function shown in figure, and what is the duration of the function when epsilon tends to 0? What is the magnitude of f of 0 when epsilon tends to 0 or epsilon is equal to 0? So this is your function. Minus epsilon to 0, you have one magnitude or one slope, and 0 to epsilon, you have another slope. So which can be splitted into the two segments, which can be written as f1 of t, f2 of t, two different functions with the peak magnitude as 1 by epsilon. I'll find out that coordinates, first function coordinates are minus epsilon comma 0, and the other coordinate is 0 comma 1 by epsilon. Y is equal to f1 of t, x is equal to t. If I find out that f1 of t, y minus y1 is equal to y2 minus y1 by x2 minus x1 of x minus x1. By substituting all these values, you'll get f1 of t is equal to t by epsilon square plus 1 by epsilon. In a similar way, the second line coordinates are 0 comma 1 by epsilon and epsilon comma 0, 0 comma 1 by epsilon and epsilon comma 0, x1 y1, x2 y2, y is equal to f of t here, and x is equal to t. By substituting all these values in the equation, you'll get minus t by epsilon square plus 1 by epsilon. So what is the area of this curve now? Area of this curve is nothing but integration of these two functions f of t, integration of f of t over the time interval. Integral minus infinity to infinity f of t into dt. But over the minus infinity to infinity, you are having only from the function is existing between the minus epsilon to epsilon only. So that can be splitted into minus epsilon to 0. You are having f1 of t into dt, and 0 to epsilon f2 of t into dt. I'll substitute this f1 of t and f2 of t in these equations. f1 of t, f2 of t. And if I do the integration, integral 1 by epsilon, epsilon is constant, integration of t is nothing but t square by 2 epsilon square, integration of 1 is nothing but t by epsilon. Substitute the limits minus epsilon to 0. In here, integral minus t is nothing but t square by 2 epsilon square as usual. Integral 1 is nothing but t by epsilon. Substitute the limits 0 to 1. If you substitute the limits, you'll get the 1. That's what the area under that curve. So here, even directly also you can cross verify, like what is the area of this curve. Area of this curve is nothing but, as it is triangle, half into base. Base is nothing but 2 epsilon into height is nothing but 1 by epsilon. Epsilon will get cancelled, 2 will get cancelled, 1. And what is the second question? What is the duration of the function when epsilon tends to 0? When epsilon tends to 0, minus epsilon will reach to the 0, plus epsilon will also reach to the 0. The duration will become 0. As epsilon tends to 0, the above equation shown in the figure becomes an impulsive function. The duration of the function becomes 0. And the third question is, what is the magnitude of f of 0? When you substitute f of 0, or when epsilon tends to 0, when epsilon tends to 0, the magnitude 1 by 0 will become, it will reach to the infinity, right? At a 0, if you are having the infinity magnitude, means that is impulse function. For an impulse function only, we'll have the magnitude becomes infinity. Therefore, when epsilon tends to 0, the magnitude of the above function becomes infinite. So this is all about the problem. Thank you all.